Okay, so I'm calling it the stabilizer problem. So there's sort of multiple meanings to that. Stabilizers have been a problem to me for some time. They are a problem in the sense of like a math problem, which is that, as I'll talk about, there's certain technical aspects of stabilizers in keyboards that have vexed me for a long time, and I didn't know for the longest time how to sort of develop a mental framework to think about that and how to solve it. So, stabilizers are problematic at many levels. The one in which they're not particularly problematic is just the simple, they do perform their core function, which is anti-seesaw, right? So we have these keys under the ANSI standard, some of which are longer than others. So the non-alphanumerics, like the spacebar, if you were to press on the far end of it, you would get this sort of seesaw effect unless we had some mechanism to counteract that, with the switch in the center acting as a pivot. And so, there are a number of solutions to this problem. The kind of standard one is this. This is a rendering by RamaWorks of their attempt at an improvement, but it illustrates the basic concept on the other side here of how stabilizers solve the problem. They use a wire linkage between two sliders that plug into the spacebar, and they pull down the other side in tandem with the others, with the long end. And so the problem, as I understand it, and I think about it, is just not performing the core function, but merely that they sound really bad. And I think this is the perfect expression of that.
Oh, come on.
Right? So this is a video that's been viewed millions of times, and it's by our colleague and friend Nathan Taeha here. And it's about what stabilizers sound like in their unlubed, natural sort of stock state. I think all of us kind of feel this way, which is, they rattle and they sound really bad. And so there's this core irony at the heart of super high-end luxury keyboards. You can spend many thousands of dollars for a Keycon board or these other sort of rare things, and they have all sorts of optimizations in them. They have leaf springs, they have gaskets everywhere, and there's like sort of hyper-engineered precision things, but they have, I think, a fundamentally flawed mechanism in them. And so, there is a kind of solution for this problem, as Nathan talks about in his video, which is we can paint lubricant into the interstices, right? And it's actually not for its lubricating effect; it's for the bulk effect, really. So the hard parts can't slam against each other if we have this sort of high viscosity grease that prevents them from touching in that same way. And the question is this like fundamental to a high-end, luxury keyboard experience, this fancy atelier process that's done by hand? Or is it really just essentially like a Band-Aid over an engineering problem? I've always suspected that it was more of a Band-Aid rather than the definition of a good keyboard. And so I kind of took a long foray into trying to understand this problem for about 5 years. I spent an enormous amount of money, trying to solve it in various ways. And my conclusion, I think, I would like to try to persuade you, is that it is the latter. It is a Band-Aid, and there is an engineering solution to the problem. I think that, the reason why I care about this is I've been developing a keyboard from scratch, where I've designed every single component to kind of express my idea of what a perfect keyboard is. It's a capacitive keyboard. It's not like a Cherry MX style board, just because that's my preference. It's kind of, I have a history of making aftermarket housings for Topper keyboards, which are kind of designed in this, this architecture that uses a rubber dome. And I've put a great deal of myself and my time and money and emotion into this project, and I just felt that this, like, the last 10% of the keyboard is the stabilizer, and it nagged at me that it was this thing that we had to kind of put that Band-Aid over, right? So I sort of delved deeply into this problem, which I'll try to explain to you a little bit. But first, perhaps we should define some terminology. I'm sure everyone in this room knows all of these terms, but we have the housing, and then the sliders that move up and down, and then this bent wire in the center, right? And perhaps less well known is this distinction of the types of sound of stabilizers. I'm kind of like formalizing a little bit of not totally formal keyboard community terminology here, but I think it works. So rattle refers to the sound of the wire moving against the interior of the stabilizer, right? And this is the one that we typically think of as the actually like very problematic one. It's the louder one. There's also this concept of ticking, which is for more subtle sound of the housing touching against the slider as it moves, and also the wire can rattle a little bit inside of the clip that holds it. And so typically, if you're very serious about lubing your stabilizers, you'll also gently lubricate those interfaces as well. And another term you sort of hear thrown about on the subject of stabilizers is this idea of loose tolerances, right? So tolerances are an actual engineering term with a precise meaning. What most people mean when they say loose tolerances, though, in the keyboard community, specifically with respect to stabilizers, is that they have loose fits, or there are gaps between the parts, right? And so it has been commonly held that this is somehow due to manufacturers just being lazy or cutting corners, and that thus one way to solve the problem would be to tighten up those interfaces, to have tight tolerances, which is associated with quality or something like that, and that the problem would somehow simply be solved. My experience, however, is that that's certainly not the case, as we'll discuss. Another fundamental problem is dimensional variability in keycap width. So particularly on spacebars, thermoplastics are molded at a high temperature, and then they sort of cool down to a normal temperature, a room temperature, and a shrinkage process happens. And so it's very difficult, especially on long, narrow parts, to control that shrinkage. And so between different manufacturers, the spacing between stems will vary considerably. This also poses a problem for stabilizers, because you need to be able to accommodate a great sort of variability in keycap widths. So you have this fundamental design tension, right? You want something that simultaneously is tight and loose from speaking metaphorically, right? We want it to move totally freely. We want it to perform its to sort of get out of the way of the switch, so that it doesn't actually impart an additional force curve or anything. But we also we want it to be tight in the sense that there aren't gaps wobbling around. But you need to have gaps in order to accommodate things like wide spacebar variation widths. In designing, thinking about what I wanted in my ideal stabilizer, I came up with a set of requirements, or sort of annoying things that I wanted to eliminate. First, of course, is rattle and ticking, the bad sound that Nathan was making his face about, right? That's the most important thing, and what I consider to be the unsolved problem in the world of keyboards and stabilizers. And again, without recourse to grease or lubrication. Why not grease or lubrication, I think is, worth considering, which is, and my answer to that is that, first of all, it's very hard to do consistently originally this was all in the context of I'm trying to make a good keyboard that I can ship to people, that would come fully assembled and ready to use. And I'm thinking about how in our workshop do we do that consistently between individuals who are assembling the keyboard, and also we found that an individual who does it will also not even precisely match his tuning of the stabilizer from one switch to the other within a single keyboard. So just from a logistical standpoint, it's kind of inelegant and annoying, which is part of it. But also it seeps away over time, so it's a thing that can require maintenance, and it's just conceptually kind of an inelegant hack. But we also need to accommodate that dimensional variability, like I talked about, without introducing binding. So again, free and smooth movement, obviously. And we also can't alter the force curve of the switch, so you don't really want your spacebar to feel fundamentally different than the rest of the board. So you kind of, as I say, you want to have the stabilizer get as much out of the way of the switch as possible, while still performing its fundamental anti-seesaw function. So and the other thing is tool-free installation and removal of the keycaps. This is another interesting problem I never would have considered before sort of delving deeper into these designs, which is when you put the keycap on to the stabilizer, you actually apply a hugely greater amount of force than you ever would when normally using it, right? So you need to have some kind of end stop that prevents that force from going so far that it just deforms the wire, right? Because, for reasons I'll discuss, the slightest deformation of that wire will introduce binding, right? So it turns out to be this very complex and competing set of requirements. But initially I was this was 5 years ago, I kind of had made my initial explorations into industrial design. I'm designing housings and stuff like that, but I have no training whatsoever in mechanical engineering. I just kind of like making pretty things, and it just driven me down various roads of exploring the technical aspects of these disciplines. And so I'm like, very naively, I'm like, well, essentially a stabilizer is a linear bearing, right? And which is to say something that restricts movement in all axes but one, and it allows one translational movement to be available, right? Or to be free. And so I'm like, I knew about these bearings that are they're called self-lubricating bearings or self-lubricating bushings that, because one of the issues with stabilizers is the extremely small space that we have available, right? So you can't use ball bearings because people do actually make ball bearings this small, but they're hundreds of dollars a piece. So 2 times 5 on a keyboard makes it just extremely prohibitively impossible. So I wanted to find some solution that would allow for low friction, but that could theoretically function as a bearing. So I had this really, on reflection, incredibly stupid and naive idea that we just simply make cylinders that we plug into the keycaps, right? And we create a linear bearing in the way that you would with a sort of a standard, let me jump ahead a little bit, this kind of a bearing, right? It's you have a carriage and you have two rods that move along a bearing. And it's a very sort of simple architecture you see all the time, like in CNC, like 3D printers and stuff like have carriages like this all the time. So I learned through this process one of the first many challenges that I would encounter, which is manufacturing parts this small with really good surface finishes and tight tolerances is insanely expensive. So these little parts here that insert into the bushings, they're like getting 6 of them made was like $1,800 because they had to be done by this like Swiss watchmaking, super specialized company that could meet the tolerances specified in the bushings, right? Because the bushing said you had to have a particular gap. And so you can see how well this initial experiment worked of my idea of creating cylinders that go into the keycaps. So obviously, not in the slightest degree does this function, right? It doesn't pop back up. It doesn't perform its anti-seesaw function. It just it's incredibly, incredibly dumb. And of course there were reasons for this, but I didn't understand any of them at the time. There's like a really fundamental concept in mechanical engineering, or a set of rules of thumb called the bearing and binding ratio. Whenever you have linear bearings, and if you violate them, you will inevitably encounter the sorts of problems that people encounter when they try to modify and improve stabilizers, which is to say that you get binding, you get chatter, and all these other issues. And stabilizers turn out to just be a particularly bad case for the bearing and binding ratio. Keyboards, we want them to be as thin as possible for ergonomic reasons, but the most important thing for the quality of the perception of a bearing is the length of the slide, right? And also the moment arm distance. This is what the binding ratio is about. So the keycap actually is significantly kind of distant from the load, and whenever you have that configuration, you tend to get binding in a bearing. So it makes stabilizers, the particular configuration and like physical constraints that we have to work in, an extremely hard problem in terms of like engineering optimization. And this is what many of my subsequent attempts at a solution would be fighting against without my quite realizing it. Just to again give some context for the difficulty of doing all of this, like here, I don't know if you can read it, but the Proto Labs quote here, these are for microfine 3D printed parts, and so just enough to fit in the palm of my hand is like $1,500 to just get a few of them. And you can't. So I got a Formlabs 3D printer for very rough prototyping, sort of things like the thing at the top right there, that's a test fixture that I used, because again, every time I would change the stabilizer, the penetration through the plate would change, so I didn't want to manufacture a whole separate keyboard just to test that out, so I have to build custom test fixtures. But something printed on a Formlabs 3D printer, even though it's pretty much the best consumer grade SLA printer, the surface finishes are way too rough. When the parts rub against each other because it's resin, they abrade each other, so it immediately starts becoming powder. And you really can't learn a lot from those parts just because it's introducing all sorts of things that wouldn't be present on the production thermoplastics, right? So if I want to render the features with good surface finishes, I have to use this really expensive microfine process. But even then, we get sort of this abrasion. So I have to like paint on see this like skull thing here. This is a material called XTC 3D, which is specifically for painting on 3D printed parts to give them a high gloss, injection molded like surface finish. So I have to sort of paint that on to get anything like the kind of slide we would get from a production part. But then that throws off the tolerances a little bit, right? So every change that I do or optimization I try to make, I'm introducing all sorts of artificial sources of friction and binding. They're not representative of the final part, which is just to set the context for how difficult it is to like prototype and approach a problem like that, like this, where the parts are so small and the features are almost microscopic, right? And this other thing here is just one of the jigs that I made for bending the wires, because every time you change the design, the wire ratio changes a little bit. And CNC wire bending companies, for whatever reason, just charge a lot of money for prototyping. And it would take like a month and $1,500 to get a set of wires. So just like it is a difficult set of problems. One of my first forays into this, weird explorations of off-the-wall solutions was materials stuff. So I actually hired an acoustics engineer to give me ideas for different types of materials that could possibly dampen the interfaces. And so I got all of these. There's this company that makes all these cool like test sample parts that have interesting features on them. And I found this kind of like fundamental, unfortunate relationship between all the thermoplastics that are available to us. You can either have good acoustics, but then have abrasion and drag, or you can have eliminate those and then you have bad acoustics, right? So I was looking for a purely material solution, originally thinking like, well, what if we made the slider out of some sort of, acoustically dampening material? Like, HDPE, for example, it's not rubber exactly, but it is a pretty soft material. So I thought maybe that plus perhaps some sort of lubrication that would be easy to apply would be one solution, but it just turns out that the parts abrade against each other. The soft plastics will degrade, the performance of their slide will degrade over time because of the abrasion. And they also just have an inherent sort of drag to them. Like you can imagine sort of, running two blocks of rubber or silicone against each other. They tend to grip each other, right? So I explored many different materials combinations, and they all would bind up or have other issues. So I even went as far as getting vacuum cast sliders in like a TPE like rubber, and it just like it was this sort of squeaky, draggy mess against the housing. It sounded and felt awful. Say nothing of the fact that you can't really push a keycap stem onto a rubber cruciform stem. So I essentially abandoned the pure materials solution and started, experimenting with mechanical design. And this is one of my early concepts of essentially using a pin joint inserted from the side, because the idea is that perhaps by having, focusing on a rotating joint, that we would be able to have a tighter clearance between the wire, and the slider, since that's the primary source of sound. And this wasn't the worst idea, and we used something like it in one of my subsequent solutions that worked much better. But the problem was, in order to get that side entry pin mechanism to work well, we had to have really large clearance gaps between the sliders and the housing in a way that like made the ticking almost so bad that it became a rattle of its own. It's like this is the minimum gap that I would need to get it to actually freely move up and down. If I tightened those interfaces at all, it would introduce binding. And this is like sort of a general theme, again, from this bearing and binding ratio that I was unaware of, which is that the main thing you're fighting with in existing stabilizer architecture is the issue of binding. Every time we try to optimize for something that we want, it has to come at the cost of binding. Whenever we tighten up the interfaces, whenever we add something that might be a materials improvement, it's such a difficult scenario for the binding and bearing ratios that any of those changes immediately push us right over the edge, because we're just kind of like, we're hovering at the edge of binding always. So this was a subsequent attempt, so we're like probably 2 years into my experimenting at this point. And this attempt was sort of a material solution. The idea was to take the wire and overmold it in rubber. since so I've gone back to this sort of normal front entry, kind of standard stabilizer architecture here, and just trying to focus on two things: tightening up the gaps in the way that like Stabies stabilizers have done, and softening that interface. There were some problems with this, namely that you still get a little bit of squeak and drag. If you listen closely, you can hear that over-molded rubber sort of moving against the slider. But if you, particularly around the wire, if you open up the interfaces enough, you can kind of save yourself some of the sort of friction and binding pressure that the drag doesn't interfere with the keycap popping back up. And you can actually also mitigate the drag and squeak a little bit if you use a dry graphite lubricant, but that kind of defeats the whole purpose of the project, because I wanted to have stabilizers that would not degrade over time as the lubricant wears away, right? So I'm fighting with all of these problems, but eventually another weird thing was when you actually overmold the rubber onto the wire, it actually slightly throws out the tolerances of the wire. You can see it's supposed to be 100 millimeters nominal, and it's slightly out of that. And just that amount of deviation is enough to introduce binding. So, sorry, to clarify, when we experience binding, basically what happens is the key just doesn't pop back up, right? It's usually not that you can't push it down. It's that it doesn't freely move back up, or even worse, it does it kind of like non-deterministically. Like 1 out of every 10 actuations, you just like hit it in such a way that for some reason it doesn't, like it hesitates a little bit, which is just a maddening problem. So it seemed to be that there's like this fundamental tension here where you can have 2 of these, but not all 3. Where we have acoustics, keycap variation support, and free movement in opposition to each other. And I think, Stabies are kind of an interesting solution to this problem, where they redefine the problem a little bit by simply getting rid of support for keycap variation and getting good acoustics and free movement. So essentially they did this tightening up of the tolerances, but they kind of just initially said, we just pretty much only support GMK keycaps, right? And I think that's one creative sort of redefinition of the problem. And with my first attempt, this is like chapter 1 of this attempted solution to the stabilizer problem, I was trying to find, like, is there some kind of center point in the middle of that triangle where I can not necessarily completely solve all of them, but find an optimal balance. And I kind of got there. I don't know if we'll be able to get sound here. Maybe if I turn my laptop up a lot. So that's an unlubed stabilizer, and that was my best attempt. Here's another one. So there's really not rattle there as I would define it. There's certainly some ticking, which you can hear. This is the one without the rubber overmold, but otherwise all the tolerances are improved. And by tolerances I mean gaps. And this is the one with the rubber overmold. So it sounds pretty good. There are other issues. You can see there's still like a little bit of seesaw wobble. But by this point, I realized that I actually had a stabilizer that without lubrication performed better than anything you could buy on the market. And it did actually more or less work. And so, I'm like, so I had to ask myself, like, is this a sufficient solution to the problem? And it's like, better was not quite good enough for me. And this is just sort of really like a character flaw in my way of approaching projects, I suppose, in that I just like, my goal was to make a no compromises keyboard. And it was greatly improved, but not a no compromises stabilizer. So, I just like spent a lot of time trying to figure out how I wanted to deal with this problem, right? And I lost a lot of sleep about it, and I held up the release of the keyboard that I've been working on for a really long time, just thinking that there must be a better way to solve this problem, and realizing that it fundamentally came down to my limitations as someone without a background in mechanical engineering, right? And I just like, after months of agonizing over this, I stumbled into a video about compliant mechanisms. So a compliant mechanism is this, it's actually they've been around for a long time, but it's kind of all the rage now in mechanical engineering because of 3D printing, because 3D printing has made it possible to prototype these types of mechanisms much more easily. But this is like the classic example. You have here like a bottle, the bottle cap for something like a shampoo or moisturizer or something like that. It's these things where there's a hinge that flexes on the back, right? And it's all one part. So it exemplifies the idea of the most simple kind of compliant mechanism you could imagine, where you have something that if it were a door, right, like with a typical hinge with rigid bodies, you would have lots of parts. So you would have the cap, and you would have the part that connects to the bottle, and then you would have a pin that runs through it, and then you have multiple leaves of a hinge. And instead of doing that, you just have one flexible part, right, or a part that leverages the flexibility of the material to perform a mechanical function and gets rid of all those extra parts and pieces. And if you think about it, this is actually in some ways the problem with existing stabilizers, right? We have multiple parts that, because they're separate, they can sort of bang against each other due to the clearance. And in theory, compliant mechanisms tend to solve these problems by eliminating separate parts and getting the mechanical movements you want through the inherent flex in the material. So I found a company that's claimed to specialize in compliant mechanism design. They're actually very difficult to find because most people who are doing this kind of work nowadays still are in academia. But I did find a company to do like a concept development for me. They were very, very expensive. They charged $12,500 to produce what is essentially this animation for me. And my deal with them was, at the end of this 1 month sprint, I need to see a prototype that at least proves the concept. But instead, all I got was this animation. And I subsequently learned that this particular mechanism is a kind of solution to the problem. Like there would be, what's maybe not obvious here is that there are these little circles that represent hinge points. The bottom right one would be a wire running from one side to the other, and so that's what sort of corresponds to the existing stabilizer wire. But it would have to be welded in place, and so this whole mechanism would probably have to be made out of some sort of metal. It would have been very expensive to produce. And the thing that they didn't realize, and that I didn't realize until later, is that this would have a variable force curve. Because of the compression of the material at the end of the switch travel, you would get this kind of like squishy jelly-like feeling at the end of the travel, which is definitely not something that we want. Right? We want the stabilizer should essentially disappear along with the switch. So obviously I didn't pay them the other $12,500 they wanted to go to the next sprint because they didn't produce anything that was a viable prototype. But I kind of, this got me interested in like, well, if I can't hire anyone to do this, maybe I could just learn to do it. So I did a lot of reading online about compliant mechanism design, and I stumbled into this company, RD8 in Denmark, who have done a lot of work for companies like Audi and Bang & Olufsen and Lego and like sort of companies that are very serious about sort of high-end engineering of consumer products. And they just happen to have a page about compliant mechanism design. And so I figured, what the hell, maybe I'll just email them and ask, could you help me with this problem? I thought they probably wouldn't even reply to a small business like mine, and that they would be fantastically expensive. They are fantastically expensive, but they did reply, and they were very interested in there's just this ridiculously nerdy problem, right? Because they mostly have clients that are making like very boring medical devices or like sort of very boring straight-laced clients, and the idea of working on this sort of very nerdy, niche, super weird, kind of almost luxury product was very compelling to them. And they got very excited about it. So, I sent them this very long brief telling the history of kind of essentially everything that I just explained to you. And they got really into it. And just after a casual call, they went off and explored lots of different ideas for how to solve the problem. But ultimately, their view was actually, they could do a full compliant design in their opinion. But their feeling was that it would take a really long time and be really expensive, and that it actually was probably not necessary. That they had an insight into what was making existing stabilizers not work well, just by sort of casually inspecting the problem, and that probably a rigid body solution, which is to say a non-compliant solution, might be sufficient to address the issue. And so they specialize in this field which originates in Japan called robust design. And there are many aspects to it, and I actually went through their course, explaining how they sort of approach product design. But the most important part for this particular issue is what they call kinematic analysis, right? So you see here this yellow box. These are like the 6 fundamental degrees of freedom when designing a mechanical system. And basically, when their sort of rule of thumb is, first you think about the kinematics, and then you think about the actual physical embodiment of the problem. And oddly enough, most engineers, mechanical engineers, formally trained, don't think in this way. So they've told me that like 90% of the designs that come to them for improvement usually haven't had a kinematic analysis. They kind of like, people will start with the physical embodiment and then work their way back to the kinematics. And they just simply go at it the other way around, sort of engineering from first principles about what we want to achieve, and then creating the absolute minimum geometric constraints that create that physical movement. I realize that's like a very abstract explanation, but I brought a couple of models from them that kind of explain the concept really well. So this is a sliding linear bearing in the same way that fundamentally a stabilizer is, right? And there are two sliders here that are carriages, like the bearing that I showed before in that black and white drawing. But they're both designed in like totally different ways. And so you can see here a 3D model of what this test fixture is. There's a blue one and a magenta one. And it's not super, let me go to the next slide. But you can see that there are different contact faces between the two examples. The magenta one is over-constrained, right? Which is to say, it was designed in that way that doesn't take kinematics into account, but merely just like sort of imagines what would be a way to achieve the slide that we want, and oftentimes does that in a redundant way. So to actually, I won't get too much into the details because it's not super interesting and it's kind of arcane and I'll probably get it wrong anyway, but in order to achieve the movement we want, we actually only need what is present on this blue slider here. So there's like 2 sets of 4 contact faces, and those prevent the slider from moving in like X and Y direction. And then we have only 2, I don't know if you can see it, but on the right here, sort of the top right, there's only 2 contact faces there. And so together, these sets of faces comprise the minimum amount of constraints that you need to get this sliding movement and no more. But the naive way to design it is to just have like 4 sets of cylindrical cutouts, as they do on the magenta example here. And so that's fine and well under ideal circumstances. If if you have perfectly manufactured, super high precision bearings, you have lubrication between the interfaces, and everything goes according to plan, the bearing ratio is good, then the magenta one will actually work, right? As you can see in both of these cases. But the question is like, what happens when circumstances become suboptimal? And as we already discussed, with keyboard stabilizers, everything is extremely suboptimal, the bearing and binding ratio and so forth. Over-constrained designs will then fail when things become suboptimal. And so this test fixture has a little switch on it, essentially, where when I move it, it takes the 2 rods, which are perfectly parallel, and it moves them ever so slightly out of perfectly parallel. And I'll show you what happens. Yeah, so if I do that, if I move the rods just ever so slightly out of parallel, one moves and the other doesn't. And so this is equivalent to the magenta one because it's over-constrained. It has those 2 cylindrical cutouts. This other one actually moves just fine. And that's because it only has the bare minimum number of contact faces that are required. And so it is robust in that sense. It is robust to variation. And this variation is exactly the type of thing that we encounter when manufacturing something with injection molded parts, and also when you have a really difficult bearing ratio situation. So, when you do the kinematic analysis of that design that I had, that like 90% good design, it actually fares pretty well. And it's equivalent to standard Cherry stabilizers. I didn't reinvent the kinematics in any way. So if you look at standard Cherry stabilizers, or you look at the ones that I created that were a slight improvement on it, they get a score of 5 on the RD8 scale of engineering, which is considered world-class engineering according to their scale. But the problem is that this is just a very challenging problem because of the bearing and binding ratio. So 5 isn't good enough. You actually need absolutely perfect so that you can surmount these other issues. And the standard architecture of stabilizers it's kinematically over-constrained. There are a number of redundancies in the constraints, particularly in these rails here, right? but they're also, like the wire constraint is also redundant. And an important part about these over constraints is they're also actually spaced really far apart. One sort of principle that I learned from them, from RD8, is that in manufacturing, if you hold the difficulty of manufacturing constant across different parts, it's possible to hold much tighter tolerances over smaller dimensions. So, we can have, it's much easier to make a 1 millimeter part, plus or minus 0.1 millimeters, than it is to make a 300 millimeter part. In retrospect, that seems obvious to me, but I just never really thought about it in terms of the a level of precision that's possible. And so therefore, as a design rule of thumb, you want to have constraining features over as small a distance as possible. But in the case of existing stabilizers, it spans this relatively pretty wide distance. And so after all this analysis, they came to me with two ideas for how to create kinematically optimized stabilizers that would score a 0 on this scale. And there are like two pretty radically different proposals. The one on the left is essentially a slight nuance on existing stabilizers. It basically deletes the over constraints and it moves the interfaces closer together, as I'll show you in subsequent slides. And so it's not like a radical reinvention, but it's just like, it's an optimization. The second one is a radical reinvention, and it involves the use of pin joints. It actually has, I think, 21 individual parts as they designed it in this initial concept they presented to me. And they were like, well, the one on the right is actually sort of the optimal solution from a mechanical engineering perspective, but it carries a lot of risks with it. We've never, first of all, I had never worked with metal pin joint parts. It obviously just looks very mechanically complex, and they weren't sure about how to simulate it. There were some complexities around the pin joint solution. The one on the left they felt confident would be one that they could solve in like a month and prototype pretty easily, and it would be a massive improvement with a total solution to the fundamental problem of rattle, which I'll show in a subsequent slide as well. And so I agonized over this for quite a while, and I decided that I'm already $60,000, $80,000 into this project, and probably 4 years at this point. And so the idea of being done in a month sounded really good to me. And so I decided let's give the left side a try because I don't want to find myself, in an endless cycle of design iterations if we go with the right one. So this is what that looks like. I call it the tongue and groove stabilizer. And you see here this is like really the core of the difference. Remember I said that the long distance is one of the most important problems we need to solve. So instead of having the constraining features span the entire slider length, we instead compress it down to this tiny little tongue and groove interface, which I think is about 1 millimeter or maybe less than that. And as a result of using a much smaller dimension, we're able to get much smaller gaps. It's not, because these are injection molded parts, due to the tolerances associated with them, it's not a 0 gap, but it's essentially, it's an almost 0 gap between the slider and the housing. So this minimizes the possibility of ticking. It also perfectly provides the mechanical constraints that we want to get the movement that we want. And also it optimizes the bearing ratio as much as is possible for a linear sliding solution. And it also, importantly, because of the way the geometry works, it allows those sliders to move in and out to accommodate dimensional variation in keycap widths. And you can sort of see in that zoom-in circle that we'll still get the constraint that we want in the right axes that we want, but we can move freely laterally. So also a very smart solution to that. And in other places we have a sort of compliant solution to issues of rattle or ticking. In this case, you have this little plastic beam in the right-hand picture that presses on the wire. And it's actually very hard to design these beams because you have to use a lot of simulation to know how to push on the wire just enough so that you keep it always in a 0 clearance state, but where you're not actually applying friction and keeping it from moving. But these guys know what they're doing, so they figured all of this out for me. And so you have, it's impossible for the wire to rattle because it's always in this preloaded state. preloaded, just meaning it's a term, it's like a specific term related to bearings when you are like applying a perpendicular force to the bearing to prevent play or rattle between it. Again, it's like a concept I'd never heard before, but very straightforward and well understood for people who know anything about mechanical engineering. So we applied the same concept to the most important part, which is the play between the wire and the slider, right? Because that is a more important part, and because there's more forces involved, we don't actually use a molded-in plastic compliant beam. We actually use a brass spring that's formed into that shape and is popped in to the slider. That brass spring then presses down on the top of the wire and presses the bottom of the wire against the floor of a feature in the floor of the slider. So that again, through the entire travel of the slider, there's never any possibility of gap because we have this spring pressing down on it. Now, if we had tried this solution before we kinematically optimized the design, it would have definitely introduced binding, because it does actually introduce some forces into the system. But because we bought ourselves some breathing room with kinematic optimization, we were able to do these things that actually would optimize for the things that we cared about. And this video here is kind of a really close-up view of what's happening of the wire inside of the slider. And so it's a little bit rotated weird, but on the top of it you can just see the spring pressing down on it. And you can see that through the entire travel, as we go really slowly, there's no moment at which the wire is not perfectly in contact with the spring on the top and the floor of the slider on the bottom. So this all worked really well. It definitely doesn't rattle. I have one of this is a 3D printed prototype of that concept. And if you hold it so that the fixture is tight, there's no rattling or any sound whatsoever. All the parts are really tightly preloaded. And the only sort of flaw in any way is just like the most minuscule gap between that tongue and groove interface. So it worked really great. We applied for and got a patent on this solution. It was approved in 3 months, where the average is 25.7. For some reason, that pleased me greatly. I was very pleased that we were able to solve the problem, and especially given that I had worked on this for years at that point. But these RD8 guys were like, yeah, sure, we can do this in our sleep, and in 2 months came up with something that was actually quite amazing. But there was, you'll notice that this is only a 3D printed prototype. It's not a production part. Because I started thinking again, I found myself coming back to this like 90% solution thing, right? I'm like, it minimizes ticking, but it doesn't completely eliminate it, right? And like, so what's the point of making the perfect stabilizer if it's not absolutely, absolutely perfect? And so I started having these like dreams about the pin joint stabilizer, and I couldn't stop thinking about it. I was like literally waking up in the middle of the night just wondering if we might not have missed the perfect solution to the problem, And so I'm like, again, this is like, it's holding up this keyboard that I've been trying to release for years, and it's the last 10% it's like the keyboard was 90% done, and then I had a 90% done stabilizer, and then another 90% done stabilizer, and I'm just like, I keep collapsing, zeroing in on my optimal solution, but somehow just never quite reaching the goal. So, I was thinking about Steve Jobs and on many projects like the iPhone, Apple Store, Toy Story, like on the eve of the release of these products, at great business cost, he frequently would just pull back and be like, wait a minute, this is not exactly perfect. What's the point of doing a project like this unless we can make it as good as we possibly can? And because I just happened at the time to be reading the Steve Jobs biography, and there's the Walter Isaacson book, and he talks about that. And I'm like, okay, I guess maybe we need to think about pin joints again. And it turns out there's a rule of thumb in kinematic design and robust design, which is the 13 different types of joints that you can create to create mechanical movements. But the rule of thumb is when you can use a pin joint, do. And there are a lot of reasons for that, but specifically in our case, the use of a pin joint would allow us to for the pin, use a stainless steel precision ground part. And that would radically transform the tolerances we were able to achieve, right? So pin joints they're stainless steel, sorry, not pin joints, but just simply pins, are stainless steel cylinders that are rolled and then ground. And so they're like almost infinitely more precise than what you can achieve with an injection molded part. And so as a result, if you create a joint in this way, you can have what is effectively a zero clearance joint between parts, and you also buy yourself really good friction because you have metal sliding against thermoplastics is very favorable in terms of friction compared to thermoplastic against thermoplastic. So this is the design that they came up with. It's this like unbelievably complex watchmaker-like design, but it has a number of like really cool features that are a part of it. And I think the coolest part of it is it kind of fundamentally redefines that linear bearing problem and kind of like projects it into 3D space. We've essentially taken the bearing and made it longer by creating something that collapses in on itself. And so we've effectively lengthened the slide by creating these features that fold down onto themselves. Again, bearing in mind the principle that the longer the slide, the better the quality of the experience. And we've molded in these end stops and everything. And the result is we have these very precision fits between the pins, which like on the right side you can see in green, those are stainless steel, and they get press fit into the joints. And so as a result, there's no play whatsoever. It like very precisely and tightly fits. But the result of this whole change of interface is that we have 1/10 of the amount of friction that we had in the old tongue and groove interface, which was already very optimized, and it kind of just entirely gets around the bearing ratio problems. It also has the added advantage that essentially we've added a second stabilizer, so it actually performs the anti-seesaw function better than traditional stabilizers. So you can see this a little bit better here from the side view. There's kind of two transverse stabilizers that operate together, and that one at the back actually ends up stabilizing better than the sort of conventional design. So we get smooth sliding. There's one case where we couldn't make everything pin joints, and so here at the front you see these little two beams. Those are preload beams like we had in the last design. So they just gently press on the wire to ensure that it's always in a state of zero clearance. So there's no possibility of ticking there. And so, this is the result 5 years later, and, I think at this point into the 6 figures of costs. But it is a kind of solution to the problem. It's a way of getting around this bearing ratio issue that's fundamental to why stabilizers are extremely hard to design. It comes with some significant downsides. One of these takes like a half an hour to assemble. There's a lot of tiny little parts. You basically have to do it with a microscope. There's 21 parts in the whole assembly, and each slider tower is a 1 cubic centimeter space that we have to pack all of these tiny parts into. So there was a lot of design time, experimentation, and iteration that went into getting everything, all of the functional features that we needed, like those end stops, into this incredibly tiny space. But the result is, a stabilizer that, to my view and by the criteria I originally established, actually perfectly does everything that we want. We accommodate dimensional variability without any difficulty. We have a perfectly smooth slide. We have no rattle. It's all zero clearance, very smooth. It doesn't change the force curve. And so this is the Norbauer stabilizer, as it were, a pin joint stabilizer that kind of is a different solution to the problem. And it's been kind of an arduous process to get here, but had I known how difficult it would have been, I probably would never have set out on the project. But now that I'm here, I'm kind of glad that this sort of random walk down different solutions led me to a place that is like, actually, I don't know, just seems pretty conceptually cool. So that's been my project. I'm happy to answer any questions if any of that isn't clear.
What's the cost for making one of these?
I don't know exactly. So what I have here, and you guys can certainly play with them afterwards, is I have in test fixtures parts made with, they're from a test mold. So they're actually production-ish thermoplastics. right? And so it gives you a sense of the performance of, one is an unlooped traditional stabilizer and one is mine, that one. And so we, oh yeah, sorry, I don't know if you can hear in the room, but so that's a normal stabilizer, that's mine. It's kind of, I realized just this last night, I shouldn't have made these housings out of aluminum because it actually imparts a little bit of ping, like most keyboards with integrated plates. So please ignore the ping, but you'll notice that rattle is not present, nor is ticking. And I think one of the most telling ways of testing a stabilizer is just to hold it up and shake it and hear if you can hear any movement, and you can't with this one. And then of course with the traditional unlooped stabilizer, there's a ton of noise. At any rate, sorry, to answer your question, I've gotten the test molds made. They alone were very expensive. But the production molds are something we're sort of kind of working out at this point. They are going to be fantastically expensive, particularly because like the housing, for example, you can see a lot of the details on there require like side actions, particularly the formation of that compliant beam that presses on the wire, which is has to be a very tight tolerance part, because if it presses too hard, it starts imparting friction and slowing down the movement. And if it doesn't press hard enough, then you'll get ticking. So we're working it out, but I'm hoping in the next couple of months or something to be able to move to production tooling and then know how much it's actually going to cost.
Are these solutions going to be easy to, say, retrofit into existing MX and electrocapacitive designs, or are they going to require boutique PCBs, plates?
Yeah, so so originally I designed this for my keyboard, and one of the requirements that I didn't mention here because it didn't seem important in general terms is that it actually had to clear my switches, which are bigger than normal Cherry MX switches, right? So the only designs that I have that like fully, or like in their fully final form are for my keyboard, the Seneca keyboard. But we've always designed it in mind with the possibility of being able to adapt it to Cherry MX boards. I've actually, ironically, until you just mentioned it, I've never thought about making a retrofit for Toper boards. But this design that you see here is actually for an MX board, because there are these, also a compliant mechanism here on the bottom is these two like little clips. So this is designed to fit into an existing stabilizer cutout for screw mounted stabilizers, and it supports like 1.2 to I think 2 millimeter thickness PCBs, and plate or no plate installations. So the idea is to just kind of like target the widest range of enthusiast MX stabilizer designs. But again, there are still some details to iron out about whether we can actually produce an MX kit for it, because I'm just really focused on for my keyboard first. But that's the idea, ultimately, is perhaps to make these available more widely. Sure?
If this is that precise, does it allow any lateral tolerance when you talk about like different keycaps?
Yeah, so this one does actually provide support for, so you're talking about like keycap width variation support, right? Yeah, so it does do that. What happens is if you have a keycap that is a little bit too tight out of the official spec, what will happen is the keycap will just sit infinitesimally smaller, to an infinitesimally smaller degree, a little bit shorter. So like not in a way that is at all perceptible, it just like slightly, pre-travels that switch a little bit so that the two stems come closer together. That's how it works. Yeah.
It seems like you've got like a bunch of hardware down here, and it's like, does that add weight to the actual stabilizer in a way that would affect the feel of the spring of the switch?
I don't think so. I mean, it's actually, I don't think that it's heavier. I haven't weighed it, but just having put together the assemblies of both, I don't think that it feels heavier in my hand. If anything, the other one feels heavier because it has the brass spring in it. And the steel pins are actually very narrow in diameter. They're 0.8 millimeters. So there's actually very little steel in the overall assembly. And I think that, like particularly on this MX version, the housing is very low profile because we wanted to be able to support plateless installation. So it's just kind of this little frame that sits on top of the PCB. So there's actually not a whole lot of plastic in it. So I can't like exactly quantify the difference, but intuitively I think it doesn't actually make it go weight.
So I guess that's worth a lot.
I think so. I mean, try it and let me know what you think.
Very early on in your talk, you ruled out ball bearings due to their individual cost
cost.
Yeah.
But also looking in hindsight to the development cost of this, would they have at least been an option for your keyboard, considering that also some of the keyboards are multiple thousands of dollars, so maybe it would have been not as relevant then?
I mean, I wasn't like necessarily conceptually opposed to very expensive components, right? Because that's what I like to play around with, right? It's just like, how can we push the boundaries of what's possible and just not care about the cost, for better or worse. And so there's another issue here, which is I just don't think it would have worked. I think I didn't understand the bearing ratio issues well enough, and I don't think that would have been enough of a solution. Ball bearings are very good in that they're extremely low friction, but I don't think that they like fundamentally solve those problems in any way, because they still have the same kinematic constraints. So my intuition, based on no experimentation, is that solution may not even have ended up working, in addition to being insanely expensive.
Are you emotionally prepared for the very real inevitability that keyboard enthusiasts are going to get their hands on this, and despite all your engineering, still insist on slathering it with lube?
Yeah, Garrett and I were talking about this earlier, because he was like, yeah, but you could just lube it, right? And I'm just because like that's become such an ingrained impulse for those of us who have been playing with this stuff for a long time. My hope is that I haven't actually tried it, because it seemed gratuitous, but now I kind of want to try it. I'm almost certain, at least in theory, it shouldn't make any difference, right? And if anything, I think it would probably have an undesirable effect of introducing drag into the system that doesn't actually solve a problem. But yeah, it's possible. I mean, by all means, I'm very pro tinkering, and maybe we could learn something by somebody discovering some other additional improvement to it. But my idea was to just have something that we could make using standard manufacturing processes that wasn't quite so fussy, and that could be more repeatably and reliably performed, so that we could deliver something that is the same experience to people, no matter who assembled it, that sort of thing.
Have you?
Patents on both the designs. Do you have any intention on making the previous design actually reality?
No, I don't think so, sadly. If somebody wants to license it and make their own version of it, by all means, feel free. I'm open to that. But it's actually like, try it out. It's very, very good. The thing that bothered me about it was almost more conceptual. It's just like that other solution would have been so cool. And like, why am I doing this if not to do super cool things, right? So it wasn't that it didn't perform well. It would have been a perfectly fine solution. But I guess maybe the patent just prevents other people from making it or something. I don't know. Yeah, there was no grand design or anything like that, or excellent strategy behind it. Just a random walk, unfortunately. Yeah, Nathan?
Have you tested the longevity of this, particularly, like let's say you have pet hair or someone who eats at their desk a lot,
right? Like
food dust starts to collect in those pin joints.
Well, so that was actually one of the advantages of the pin joints over the other solutions, is that it's less prone to that, because there are no openings, right? The tongue and groove does theoretically have a gap, and you can get dust in there that could introduce that. But the pin joints are such tight fits that it's essentially zero clearance, and so it's very difficult for anything to get into them. It would sort of gum up the works. I haven't actually, one thing I'm looking at right now is building a test fixture to actuate these over, hundreds of thousands of actuations and see what happens. But as I say, this was kind of like a child's play kind of project for the guys at RD8. So they're like very comfortable with the performance and how they think that it will behave over a long period of time. And so, I'll take their word for it. Of course, as usual, if like there's something wrong with the performance of it, I would probably just fix it and replace it. But some of these things you never learn until you actually release it into the wild, like the ways in which people will abuse something, or things that you need to be robust to. And so my goal has just really been to like, let's solve this problem and get it out into the world as quickly as possible. But at least in theory, this should be better than other solutions for that reason. Back there?
So you mentioned that the perfect stabilizer was the last sort of hold off before your perfect keyboard came out.
Right.
Now that you've solved that solution, about how far away is the Norbauer perfect keyboard?
Well, bearing in mind that perfect is an extremely subjective thing, right? But it's my expression of the idea of perfection. I think so. Probably we're probably going to do like a pre-order offering to some existing clients in the next few months, and then the goal is to try to ship it maybe the end of the summer, the fall, and then have wider availability after that. So before the end of the year. We're finally super close, and there are many things that I haven't even talked about in this talk that went into the making of that keyboard that were not as hard, but in similar ways hard to this. So there's actually a little detail in this drawing. We just filed a patent for it yesterday, which is, you'll notice that the stems are not normal cherry stems. They're kind of like, we call this the bird stem because they have these little 2 wings on the side, and it's meant to address the problem of retention force degrading over time with multiple insertions and removals of keycaps. They tend to just they become loose over time, and this uses another compliant mechanism to solve that problem. Instead of digging into the plastic, it just kind of flexes out of the way a little bit. And so as a result, it should have a very consistent retention force of keycaps, no matter how many times you remove and put the same caps on. And they don't leave drag marks. If you look under a microscope, normal crush ribs on a lot of switches will leave linear drag marks, which is where that phenomenon comes from, and ours don't do that. So there's lots of there's a million little things like that, and so I'm still dialing in some fun improvements that I want to include in it, but I'm really very committed to actually shipping these things very soon, or I'll go absolutely insane. So. In the far back, yeah.
When you talked about the keycaps being out of spec, slightly, being slightly too short,
yeah.
And that forcing them just a little bit down, is that just because the sideways pin joints are being forcefully actuated just that tiny little bit?
I'm sorry, I didn't fully understand the
Like you
concept.
said that keycaps that were too short would be just infinitesimally smaller, or sit shorter.
Oh yeah, so on the final stabilizer design, yeah.
Is that just because those pin joints that are facing long ways down the cap, is that just because those are getting turned just a little bit by the cap being too short?
I think just the way the mechanics works is that when you even without a keycap on it, if you were to press those stems apart from each other or towards each other, it actually just naturally begins to the movement of the switch or of the stabilizer, and I think that's all that it is.
Yeah, you mentioned that current materials are plastic and steel. Have you considered all steel or all other materials and different combinations?
I mean, you mean for this particular solution, the final solution? I think actually this particular combination is considered to be essentially optimal because you want different, for good sliding properties, you want different coefficients of friction. So and different materials. And so the plastic versus steel is what they would have chosen anyway. It's not just because that was a readily available process that we were using anyway. I think that if we had, for example, 2 metal pairings, that would actually be worse from a friction standpoint. It's kind of I did occasionally look at doing parts in, for example, my switches or components of this stabilizer in metal, because that acoustics engineering consultant that I hired originally suggested that entirely metal parts might have better acoustic performance. And there turns out to be ways of injection molding metal parts to reasonably tight precisions. They actually they mix it with a polymer and then they somehow burn out the polymer or something. It seems to me like it would be a very low tolerance process, but in theory, I think it's just called metal injection molding. In theory, you can create parts to the same level of precision or better with metal as with thermoplastics. But I'm not sure that I would actually be any better other than for other acoustic considerations that are no longer relevant in this case because we've eliminated the source of sound. Anything else? Did you have a question, Mario? Okay. All right, well, there you go. Stabilizers for you.
I still have my sticker on. I don't even
I do like the stabilizers.
I mean, they're definitely insanely rattling. For some reason on the HHKB, it doesn't seem to matter as much. I don't know why. It's just like that's just how it is. That's what the board is. That's how it all.
Yeah, I have Deskey's
I've done it, and I was like, I instantly took it back off.
moved
I was
it.
like, this is
CK
wrong.
ultralight down.
Have you seen Chicken Man's Pro 2 that's out there?